All right, I hope everyone's doing good today. Um, Welcome back to day two. Again, once you all get into the stream, go ahead and put something in the chat. Let me know that people are getting here and that we have everyone watching. Yeah, also for attendance. Absolutely. Excuse me. How are y'all doing? Everyone doing all right? I'm doing good. Still adjusting to a schedule that has me getting up early every day compared to the summer when I was sleeping until 11 o'clock every day. So, but yeah, doing fine. How was your class yesterday? Your 1324 class. Okay. And if you miss Monday, you can still go back and watch the video and get caught up that way. Were there any questions from either Monday's class or Tuesday's class that you wanted me to go over? I didn't assign any homework for Monday, but we did talk about a lot of different concepts regarding fractions, and we'll continue from there today. Okay, I'm not seeing any questions, so that's hopefully a good sign. But it is just the third day of class, so we probably haven't given a lot of homework yet, anyway. So that's a good thing. Anyway, we'll continue today working on uh, kind of our introductory topics and just kind of the essential skills that we need for the course. Pop-up browser thing is so annoying with Pearson's website. It I finally fixed mine, but it took some effort. If yeah, what we're doing in this class is we're working on kind of the basic skills that we'll need as we move further into the course. It's not anything that we necessarily need right now, but just skills that we'll need to be successful throughout the course. That's why we started with fractions and things like that. But yeah, it's not really connected to sets and Venn diagrams, uh, which is what y'all were doing yesterday. Mhm. Now, I set up classes for my algebra and statistics courses, but y'all aren't even able to get to this point. Is that what you're saying? Now, are y'all trying to use MathLab through Canvas or through just Pearson's website like I'm at right now? Through Canvas? One thing you might try before you try to access it through Canvas is to come here and sign in. But you'll have to register as a student first, of course. I don't know if you'll need to do that first. I'm not that familiar with Pearson, but I always use it from just the website here. And then once you sign in, then you can just go into your course, and then you have your ebook there. We're talking about Canvas and getting logged in, Zoe. Anyway, let me see. And actually, I don't think I can do it for your course. Hmm. So once you get to this point, this course we'll go over some of the same material later, or not really the same material, but things that will help you learn that material better. And if you do have questions in the other from the other course, I can go over those and help y'all work on those too. So when you get into Pearson, as you go through the different pages here, um, you should have an access code already from when you purchased the book, and then you can just click here on access code, and then you'll be able to follow the instructions here, and that would help you create the account here. Um, if that's not working, uh, if that's not working, then I'm not sure what the issue is. What I'm going to do with homework is I won't actually assign it out of the book unless, because here's one of the amazing things about my math lab and so on is Mrs. Nicely tried to add me to her class when we were having a meeting last Friday, and and she wasn't able to do it, and we still don't know why, because I'm signed up as an instructor, so she should be able to add me to the course. So I'm not completely sure what the issue is there. Um, so I may not be able to use the same course that she's using. So what I may do instead is create a separate one. Um, I'm still trying to figure that one out, to be honest. So anyway, once I get that figured out, I'll definitely let y'all know. Um, but you should have this course, Mathematics with Applications, and it's by Lyle and Hungerford, and that is the 12th edition. So, um, that should be the book that you got, James. I'm not sure what the concern is there, but I think the good news is you still be able to exchange that for the correct one. Yeah. Now, for my course, I don't really mind if you have the physical copy or the ebook with the access code. But I would go with whatever Mrs. Knisley says, because she's going to have probably a lot more stuff going on with the ebook. Um, so be careful about that. Yeah, and what I could do. Let's see. Not add quarter. Sorry about the delay here. What I can do is I can go through and create a course as well, and I may actually assign some problems here, but it'll be out of like the earlier chapters that we don't actually cover in the main course. And this is to help us prepare for the main course for the 1324. Okay. Apparently, I'm not going to do that right now, so I'm just going to ignore that for the moment. Okay. Anyway, yeah. So we're kind of still dealing with some of these first of the semester issues, as always, and part of it's on the technology side of things and so on. Um, when when if I do put homework up on Canvas, it won't be in the same section as Mrs. Knisley's class. It'll be in the other Canvas course that's connected to the 0424 class that we're in now. So there's 1324 and there's a 0424 section, and you're enrolled in both of those, but the homework will be listed separately. So you'll have to go through the other Canvas course, not the 1324, but the 0424. But when I create that assignment, it should show up on your as a notification in your courses. So hopefully that'll be something you recognize. Were there other questions before we get started? Yes, and once I get the course created in MyMathLab, I will make sure to post the course ID in an announcement on Canvas. That way you'll be able to find it and apply it. Well, I don't stream anything on this channel just besides the teaching. I have a separate channel though. I'm not gonna give it away though. I'm not sure what's going on with the student IDs, Luke. We got an email yesterday about it that they're still working on it, but I'm not sure about the logistics of that whole thing. I'm hoping y'all get student IDs. If it comes to where you don't have a student ID and you need to do like a proctored exam, I think in most cases they'll accept your driver's license as a valid ID. So I wouldn't worry about that too much unless you don't have a driver's license, I guess. But you need some kind of state ID, even if you don't have a driver's license, I think. Yeah. Okay. Alright, so last time we talked about fractions. This time I wanted and a little bit about decimals, but I think most of you are okay with that. Today I thought we'd begin with exponentials and radicals. And this is actually section 1.5. Okay. Now let's start off with just exponentials. Or exponents, if we want to call it that. Exponents, the idea is that we have a number raised to another number. So we see a 2 and then a little 3 as a superscript here. So in this case, 2 is called the base, and 3 is called the exponent. Okay. And what that actually means is if we have 2 to the third power, that means we want to multiply 2 times itself 3 times. Okay? So 2 times 2 is 4, times 2 again is 8. And that's easy enough, but that's just the general process that we have there. So, if we have six squared, for instance, that means 6 times 6, so that'll be 36. If we have 4 to the 5th power, 4 times 4 times 4, all that 5 times, and so that is 1024. Now, that's great if we just multiply it out like that, but ideally we'll just be working with this. We won't actually be completing the multiplication, and that's where the calculator comes in handy. So on most calculators we usually have some kind of button. Here on this calculator it says y raised to an x, basically. So what I'll do on this calculator is I'll take 4, I'll hit the y to the x button, and it enters a caret up there. Trying to get a good location for that, sorry. There's not a good location for that. And then I'll enter 5, and it'll give us the result, 1024. So, we can do, we said 2 raised to the 3rd earlier, 8, and the calculator is able to complete these for us. Now, depending on the calculator that you have, you may have a different button. For instance, I would check with Mrs. Knisely, but I'm pretty sure we do not want children using graphing calculators. But again, I would check with her, because it's ultimately her class you'll be taking tests in, not mine. Okay. And she said no graphing calculators. Great. Yeah, so no, you won't be able to use a graphing calculator. Some calculators have here, I have an x with a box in the exponent. So for this one, if we did 4 to the 5th power, it's still the same approach. We hit the base first, then we hit the exponent button, and then we enter the exponent, and finally enters or equals, whoops, and it gives us the result. Okay. Other calculators, and again, this is a graphing calculator, but notice this one has a caret, so that's another way you'll sometimes see the exponent button presented. It just depends on the brand and the variety of calculator that you have that you're working with. Anyway, I'll primarily use this one, mainly because I like it better than the others. I've used it more often. So anyway, when we do these exponents, and whenever we get to like the financial mathematics chapter in the other course, in the 1324, that'll, in some cases you'll end up using pretty big numbers as your exponents, and that's why the calculator is important. These operations here, we don't need to use a calculator really to figure these things out. We can just multiply it out as is shown. Yes, it was, Gabe. But again, we're not going to be able to use a graphing calculator here, so I wouldn't worry about it. We use that for our statistics class. That's why I have it here on my desk. So for exponents, sometimes we'll have to include decimals as part of these. For instance, what if we said 1.23 raised to the 50th power? And this is kind of similar to what we may end up doing in some of those application problems in this course. So the approach is the same as far as using the calculator. You put 1.23, raise it to the 50th, and it's going to give us a pretty big number as a result, as you can imagine. This one turns out to be 31,279. .19532. Now, in a lot of cases, we may not want to include all of those numbers after the decimal. One of the guidelines that we sometimes follow, especially if we're working with values that represent money specifically, is anytime we work with prices or values of things in like U.S. currency, we like to go to 2 decimal places. So if we want to round to 2 decimal places, what would be the decimal in this case? Two places after the decimal. So essentially, what are these 2 numbers I would write down here? 0.20, good. We see that we have at the second decimal place we have a 19 here, and our thought is certainly, okay, well, we'll just put 19 down there. But because the third decimal is higher than, is 5 or larger, that means we're going to round this up to the next level, which would be add 1 to the 9, which makes it a 0, and then moves that to a 2, basically. So 19 plus the extra 1 will make it up to a 20. Right, because of the 5, we do end up rounding that up. So really, we're actually looking at the third decimal as far as how that affects the second decimal. So if this is representing a dollar amount, then yeah, we definitely want to round it to 2 places. In some cases, we may want to round a little bit further, but most financial applications are dealing with some kind of dollar amount, so 2 places is sufficient. There are other guidelines that we sometimes use, such as significant digits and things like that, but for our part in this class, it's really just, for financial amounts, we'll use 2 decimal places, and depending on what kind of data we're working with, we may change that if it's something besides like dollar amounts. Okay. So, continuing, we also may have, and this is rare actually, but we may have a decimal number in the exponent also. I don't think so much in this class, but overall we might. So if we wanted to perform this operation, again, we'd take our 1.025 and raise that to the 21.3 power. And again, we get our number, and this one's well, it's not that big, but oh, I'm sorry. I'm off the screen. Thank you, Mary. But we end up with 1.692. So what would that number be if we round to 2 decimal places? .69. Good. Yeah, this time, because the third digit is just a 2, it's less than 5, so we're not going to round up here. We'll just basically truncate the number and cut it off at where it's just 1.69. Alright. Now, there's other operations that we can do with exponents. When we say operations, we mean like the basic arithmetic operations, like adding, subtracting, multiplying, and dividing. Now, exponents, we don't really add and subtract a whole lot, because in that case, we just calculate the value and do the addition or subtraction. But the multiplication and division is where we want to pay a little bit more attention. And so the idea is, what happens if we take 7 and raise it to the 5th power times 7 raised to the 6th power. The question is, how do we rewrite this answer as 7 raised to some power? Okay. And the question is, which then becomes, how do we deal with these two different exponents? Well, if the bases are the same, which we see both numbers have a base of 7, then it turns out that we can multiply these two together, or the result of multiplying these two things together is that we add the two exponents. Yeah. So we add the exponents, and so that's going to make this 7 to the 11th power. If we think about that, when we think of 7 to the 5th times 7 to the 6th, that means 7 to the 5th is 7 times 7 times 7, 5 times. And 7 to the 6th is basically, oh, there we go. 7 to the 6th would be 7 repeated 6 times. I'm running out of space. Okay. And combined, this is 7 multiplied by itself 11 times. And that's why it ends up being 7 to the 11th power. So we have basically 11 of these 7s multiplied together. Now, again, we don't have to write it out like that. We know the rule is that, if we have whatever the base is raised to x, let's not use x, let's use m. times the same base b raised to the nth power, then we combine the two exponents by adding m plus n and keeping the base the same. Okay. So we add the 7 to the 5th times 7 to the 6th. We kept the 7, but then we added 5 plus 6, and that gave us 7 to the 11th power. And that's the rule that we're applying. If the bases are the same, we add the exponents. Okay. So, what if we have 5 to the 10th power times 5 to the negative 3rd power? What would that be? Five to the 7th. And what if we had 4 to the 2nd power times 2? Well, let's not say 2. Let's just say 3 to the 2nd power. Can we combine those into a single term? No idea? Okay. Yeah, the base is different, so we can't use that same rule to combine these together. What we could do is we could say, okay, 4 squared is 16, and 3 squared is 9. And so we end up with a result of 144. What's happening, Sylvester, is there's a delay from when I see, like from when I write things down to when y'all get it, and then there's another delay, like when y'all type stuff in to when I get it. So combined, it's anywhere between 5 and 10 seconds. So there's a slight delay, so I apologize if that's being confusing. Generally, yes, Luke. Although there's actually something else that we can do in this specific case, it turns out. Because in this specific case, because both of the exponents are 2, if we have b, base b to the nth power times base c to the same power, so if the powers are the same but the bases are different, then we can actually multiply the two bases together and then raise it to the same power. And the idea is that if the exponent is the same, then essentially we can factor that out. It's not really factoring though, it's kind of rewriting or reassociating what the order of operations. Okay, so if we had said, for example, 3 to the 4th power times 2 to the 4th power, then we can write that as 3 times 2 in parentheses to the 4th power. Exactly, Luke. This would actually be 4 times 3 is 12, and then squared, and that's again corresponding to 144. Okay. So we actually have a lot of different exponent rules. So that this is our second rule regarding multiplication, is that if the exponents are identical, then we can combine the bases accordingly. Okay. So continuing, for this next example, moving past just basic multiplication of two terms, here we have a single base raised to a power and then raised to another power. Now, certainly we could do this one step at a time. We know 3 squared is 9, and then we can find 9 to the 4th, which is much larger. I think 65, 61. Yes. And so, we can work it out that way. But there's another property that we can apply here, and that is that if we have these two exponents, 3 raised to one power then raised to another power, we can combine by multiplying the exponents. So what would that be equivalent to? 3 to what power? Eighth. And then we could put 3 to the 8 in our calculator, and it should give us the same result. Okay. Now, let me do one more example there. We have a 10 raised to the square and raised to the 6th power. So that would be 10 to the 12th. Okay. And then from there, if we wanted to write out the answer, that'd be a 1 with 12 zeros after it. Which in the US, we refer to that as 1 trillion. Other countries you may find call that a different number, which is probably confusing. But yeah. Alright. Yeah, the nice thing about 10 being raised to a power is that the power in this case indicates the number of zeros. Okay. So let me throw out another example. Four to the fifth power times 2 to the third power. Now at this point, we haven't really, looking at these two pairs of terms, or this pair of terms, none of the rules that we've looked at so far can really be applied here. We do not have the same base, nor do we have the same exponent. So we can't combine the bases, or we can't combine the terms by using either of the two rules that we looked at so far. Nor do we have this situation. However, because we're working with a 2 and a 4 here specifically, we can rewrite this 4 so that it has a base of 2 instead of 4. Can we write 4 as a power of 2? Yeah, we know 4 is 2 squared, exactly. And so we can take this expression and change the 4 so it's a 2 squared. Okay. And then 2 squared to the fifth power, we can make that into 2 to what exponent? Ten. Yeah, because if we have something raised to a power raised to another power, we multiply those two powers together. So that's 2 to the 10. Okay. You see why, Gabe? And so now we need to multiply these together, so it'll end up being 2 to what exponent? $13 will be the exponent, yes. But notice that when we had two separate terms, we didn't multiply the 2's together. We left the base the same as the 2's, but we only add the exponents together. Okay? And so that's our result, and we could then go into the calculator and calculate that out. And that ends up being 8,192. Yeah, so, and what I'm trying to illustrate with this particular problem is the difference between when we would multiply exponents versus when we would add exponents. We have a single term, raised to a power, raised to another power, so we multiply those two exponents together. But now with two separate terms at the same base, now we add the exponents and keep the base the same. These are very important distinctions, but we have to be able to recognize them and apply them properly whenever they come up. Yeah, if this 4 hadn't been a power of 2, then we wouldn't have been able to do anything with this particular example. If this had been a 5 instead of a 4, we would have just did raise this to a power, raise this to the power, and then multiply them together. Exactly, Gabe. Yeah. Mm-hmm. Now, I'm not saying we couldn't get this number by just doing 4 to the 5th, 2 to the 3rd, and multiplying those two numbers together. The whole goal here is to understand how these exponents interact with each other. Okay. One more rule that we want to look at here regarding exponents, and that is, what if I meant that to be the same number top and bottom. So if we have, for example, 7 to the 5th power divided by 7 to the 3rd power. Well, when we multiplied terms with the same base, we ended up adding the exponents. So if we're dividing terms with the same base, how do you think we combine the exponents in this case? Subtract, yes. So what we can do is we can take the number on the exponent on top, 5, minus the exponent on bottom, 3. And so that'll give us 7 squared. And that much more simply works out to be 49. Mm-hmm. Mm-hmm. Yeah. And 7 to the 5th, that's a pretty big number. 7 to the 3rd, that's a big number. But it actually comes out to a very simple number, because a lot of it just basically goes away when we simplify them. And again, the idea in this case is that we have 7 times itself 5 times, divided by 7 times itself 3 times. And so essentially what's happening here is we're canceling out each 7 that's in common, and then there's 2 that remain, so we still have 7 squared, or 49. And that's an excellent question, Zoe, because I'm going to do that in my very next example. So we'll talk about that in a moment. Yeah, if let me go ahead and show you an example before we dive into this much further. And so the question is, what if the exponent's bigger on the bottom, like 4 to the 6th divided by 4 to the 8? Well, we still subtract those. the principle still applies. So 6 minus 8, that'll be 4 to the minus 2. So yes, we do get a negative exponent. Excuse me. So with this negative exponent, the question is, what is this going to be equal to? Well, it turns out it's going to be a fraction. May not be immediately obvious what that is, but let's look at the other form, because if we have 4 times itself 6 times on top, and we have 8 4s being multiplied together on bottom, all the 4s on top cancel with most of the 4s on the bottom. Now, when we cancel these out, what number would be put in their place? What is 4 divided by 4? Yeah, 4 divided by 4 is 1. So technically, when we cancel out all these 4s, there's still a 1 in the numerator. Yeah. And then on the bottom, we'll have 16, because we have 4 times 4 still. So it turns out that 4 to the minus 2 is equal to 1 over 4 squared, which is equal to 1 over 16. Okay. This is where it's a little bit more confusing for a lot of students, so it's okay if you're not quite sure about this right away. Negative exponents are really kind of a strange thing, but it's something that we have to be aware of. It's something that does come up. So, let's look at another example. 2 to the third divided by 2 to the sixth. First of all, what would this exponent be after we subtract? Negative 3. Okay. Now, without doing all these steps that we had talked about before, the question is, what would this be equal to? Well, one approach that we can take, and I like this as kind of a common sense approach, is if we have a negative exponent, the negative basically says, what's a good way to say this? It is 1 over 8, that's correct. Yeah. But the basic concept is that if this is 2 to the negative 3 in the numerator, then it will be 2 to the positive 3 if we take this term and flip it down to where it's on the denominator. By changing an exponential's location in the fraction from the numerator to the denominator, it basically changes the sign. And so this is equal to 1 over 8. Okay. So if we have 2 to the negative 3, we move it down to the denominator, that changes it to a positive 3. Basically moving it from one side of the fraction to the other flips the sign to the opposite. Now that brings up a related question. What if we have 1 over 4 to the negative 2. What would that ultimately equal? Because what we can do is, because it's in the denominator, we move this one down, and that changed from negative to positive. This one, because it's negative in the denominator, we'll move it up, and that'll make a positive exponent in the numerator, which we can just calculate out is 16. Okay. So by shifting where a term is in the fraction, it changes the sign of the exponent. Notice, though, that the base doesn't change in this process, only the exponent is changing. This can be a little bit confusing, so please let me know if you have any questions. Luke, it depends on the signs of the exponents. And I think you might have it backwards, but again, it depends if the exponents are positive or negative. Yeah. Like our previous two examples, here we had the larger number on the denominator, and it ended up being a fraction. Larger number on the denominator ended up being a fraction. Now this one, we only really have the 4 to the negative 2, but negative 2 is negative, so technically it's smaller than not having an exponent at all. If we don't have an exponent, we assume the exponent is 0. And negative 2 is smaller than 0, and then it does become a whole number in that case. So just to summarize these two rules, if we have base b raised to the m power over base b raised to the n power, then we just subtract the exponents. The other rule I presented is that b to the negative n is equal to 1 over b to the n, and 1 over b to the negative n is equal to b to the n. So I guess 3 rules there. Now, we've been working with each of these rules with just basic numbers, but it turns out that the same rules apply to if we have variables. So let's start introducing some variables here. For instance, if we have x squared times x cubed. Now the x is the base in this example, so what does that turn into when we combine them together? It'd be x to what power? Five, right. And it's 5 because we add the exponents. And again, to contrast that, what if we said x squared in parentheses to the third power? Here we multiply in this case, so it'll be x to the six. Now, when we look at these two problems side by side, and again, it shows that distinction that we have to be mindful of when we see these problems. If we have two different terms with the same base, we add their exponents. But if we only have one term, but it has two different exponents being applied, as we have in the second example, then we multiply those two exponents. So that's really the biggest concern, is knowing when we add the two exponents versus when do we multiply the exponents. Okay. What if we have x to the 17th divided by x to the 12th power? Would it be negative 5? Or positive 5? Remember, we're taking the top number minus the bottom, so yes, it would be positive 5. Okay. We could have two different variables and raised to a third power, for instance. We could say x squared times y cubed in parentheses to the fourth. Now, exactly, Gabe. If the exponents were switched, it would be a negative 5. Because instead of 17 minus 12, we'd be doing 12 minus 17. Okay. So in this instance, we know we can't combine these two terms, x and y, because they have different bases. So we don't need to worry about that. But we do want to take each of these that are inside these parentheses and raise it to the fourth power. So we can think of the fourth power applying to each of those terms inside. So that would be x squared to the fourth times y cubed to the fourth. What would that give us? X to the 8 and y to the 12th. So in this case, we can't combine the two terms inside the parentheses because they're different variables. And that's one thing that happens with variables that may or may not happen with numbers, that we just can't combine them. Oh, that's fine. I know what you meant. But the 4, because it's on the outside of the parentheses, still has to apply to both parts. So we take the x squared and raise it to the 4th power, and then we take the y cubed and raise it to the 4th power. Okay. The operations where we have variables are basically just like when we worked with the numbers, but again, we can't combine the different variables together, so we have to treat them separately if we have like an x and a y like we do here. That's the only thing that really changes when we have variables instead of just numbers. Okay. Now it's possible that we have something like this. That's a good question, Gabe. What if there was a plus between the x and the y? Then we would have to actually go through and multiply the binomials together, and that'd be a much more complicated problem. I'll show you one like that in a second, but maybe with smaller numbers, so it's a little bit easier. So what if we have 2x squared to the 3rd power? Well, the way we work this one is really the same as we worked this one. We're going to take the 2 and raise it to the 3rd power, and we're going to take the x squared and raise it to the 3rd power. What does that give us? Close. First number is not 6. 8. Mm-hmm. 8x to the 6. Mm-hmm. Yeah, because 2 to the 3rd power, we can go ahead and make that an 8. And then x squared raised to the 3rd, we have to multiply these together, so we end up with a 6. Okay, this is the other question that we had. What if we have a situation such as this? Instead of being multiplied like these two were, we have addition instead. And I wanted to make a more simple problem than the other one, just so it'd be easier for us to do, because this one, if there had been a plus between those two, would be a much more complicated problem. But we'll see why in a second. So with x plus y squared, anytime there's a plus here, we can't really do the same approach that we were doing up here. In this case, the square means that we're actually multiplying this times itself. I mean, and the 4th power means the same thing. We just have this 4 times. But the difference is, with these being multiplied, when everything's multiplied together, we just multiply it using the addition rule. With the addition of the exponents, sorry. When the addition is here between the terms and then being raised to an exponent, we actually, in this case, have to go through and FOIL the terms. In the FOIL, once again, we do the first term multiplied together, which is x times x. X times x is x squared. We do the outside terms, x times y squared. We do the inside terms, and we could say y squared times x, or we could say x times y squared. I would recommend keeping that as xy squared because we can combine these two together. And finally, y squared times y squared. If we multiply y squared times y squared, what would that equal? Y to the 4, right. You almost had it, Gabe, just this last term. Yeah, and so we would have our x squared. We'd go ahead and combine these middle two pieces. So we have 2x y squared, and then plus y to the 4. Okay, and so it really does make a difference if we have a plus between them versus a times. For now, we're really only concerned with when they're multiplied together, but this case where there's a plus instead of a multiply, certainly something we should be aware of. I think we may or may not cover that in a later section. Okay. Now, the other topic that we have today is radicals. That's correct, Gabe. They're not the same. Okay, and so when we talk about radicals, generally we mean roots of expressions. So it could be a square root, so if we said the square root of 4, okay, normally we would just put our radical sign, which is this figure here, and then 4. And because it's the square root, there's actually an implied 2 that's there. So when we don't write a number, we know it's actually the square root. So it's the second root, or just the normal radical of 4. And the square root of 4 we know is equal to 2. We could say the cube root of 1,331. Now when we use the cube root, we have to put the 3 there. Okay. Only the square root can we get away with not putting a number in that little V shape there. If it's cube root, then that means the third root. So we'll put a 3 here. Now, on your calculator, it's hard to see. It's very hard to see. Oh, I don't have it, that's why. Okay. Sorry about that. Now, on some calculators, you'll have square root, excuse me, and then above it, like on the second row of operations where you have to press second or shift or whatever you have, there'll be like a cube root here. Now, in my calculator, the cube root's actually over here right above x cubed, which is not terribly out of the question. So I would enter the cube root and then 1331, and we get a value of 11. Okay. So if we wanted the square root of 576, we could enter that in and get a result, 24. One of the things that you may notice when you're using your calculator, on mine I had to press the square root first and then entered the 576 and then equals. On other calculators, you may need to put the 576 first and then press the square root button. For instance, on my phone's calculator, for instance, I would have to put the 576 first and then press the square root button, and it would give me the 24. So it's in the opposite order of how I did it on my other calculator. So part of this is really just familiarizing yourself with your calculator, and I would recommend you do this with the calculator that you plan to use on each of your tests this semester. That way you know how to use that calculator and you're ready to go for those exams. But anytime you do have a calculator question, it's a little harder for me to answer if I can't. You can't just show me your calculator and I can point out what you need to do in person. But if you want to take a picture of your calculator, then I should be able to see what is going on in some cases, or hopefully point you in the right direction. It just depends. But the main thing is that we figure out how to use these calculators to help us answer these questions. Okay. Now with radicals, we have some different properties that we can apply. Let's see. For instance, if we have the square root of 8 times the square root of 2, if we have a product of two terms and they have identical roots applied, we can make that the square root of 8 times 2 in this case, which gives us the square root of 16, or simply 4. So as long as these are the same root, we can combine this together to a single root. Okay, so our rule is the square root of a times the square root of b equals the square root of a times b. Now, the great thing about this rule is that not only does it help us combine two roots together, we can also take an expression that's together and split it into two pieces. For instance, if we have the square root of 40. Now, you may go into your calculator and find square root of 40 is not a whole number. It's 6.32, and it keeps going from there. But we're not necessarily interested in writing down 6.32 and so on. We're more interested in applying our rule and showing how these different values work together. So the idea is, can we think of a way to split up this 40 number into a pair of numbers being multiplied together, where one of them is a perfect square. What would be our factorization of 40 that would work best in that case? Four times 10. Generally, we would like to pick the largest perfect square possible. In this case, 40, we really only have one perfect square, 4, that is a factor of that number, so it's a pretty easy choice in this case. So what this same rule tells us now that we have a square root of a product, we can split that up as a product of two square roots. The square root of 4 times square root of 10, and so we prefer to represent this as square root of 4, which is 2 times the square root of 10. Now, the problem if we use 2 times 20 instead of 4 times 10 is that neither 2 nor 20 are perfect squares. In that sense, we mean that we can't get a whole number square root. Now, square root of 4, we were able to complete that and get a 2. But we wouldn't be able to do that if we have 2 and 20, because neither of those numbers has a precise whole number square root. And that's what we're really working towards here. Because when we simplify square root of 40, we want to have as small of a number as possible left under that square root and bring out the whole number portion that we can get. Exactly, we're looking for the square root. So 32, this is another number that has, it's not a perfect square itself. If we take our square root of 32, it'll give us 5.6 or 5.7, something like that. But we can split it up into two numbers where one of the numbers is a perfect square. Now, actually in this case there's two different ways we can split that up, but we want the perfect square to be as large as possible. So we could start off 4 times 8, exactly, because 4 is a perfect square. There's actually a bigger number that's a factor of 32 that is a perfect square. 16 times 2, yeah. And we may not recognize our multiples of 16 because certainly it's not something we study when we learn multiplication tables, but 32 is definitely a multiple of 16. And so we can split this up to where it's the square root of 16 and square root of 2. Why would 4 and 8? We could do 4 and 8, but the problem is if we split this up as 4 and 8, 4 is a perfect square, and that's correct. But 8 still contains another perfect square as a factor. So we haven't completely split it up the way we would like. I'll show you in a second. Let me finish up with this. So the square root of 16, which is 4, and then square root of 2. Is that what you meant when you said 4 and 2? Okay. So what I think the question is, why didn't we go 4 times 8? Well, we could do that, because we know we can certainly get a square root of 4 as 2. But the problem is that the 8 itself can be broken up further. So 8 is itself 4 times 2. And so we can split that up again. And go ahead and make square root of 4 2 once again. And we still have square root of 2. And we would multiply these two numbers together that are on the outside. So that is 4 times the square root of 2. So that's the same result that we ended up with. It did take a little bit more work, though, because using 4 and 8 works, but it's not the optimal choice, I guess I would say. And it's okay if we do that, but we'll make it much easier on ourselves if we recognize that 16 is a factor of 32 also, and it'd be a much better number to factor out. Now we also have a rule for division that applies in basically the same way. So we might have, for instance, square root of 96 divided by square root of 12. And the reasoning here is that we can go ahead and combine them together by dividing. Essentially, because they're both have the same radical, we can make that 96 divided by 12 inside a single square root. And so I'm using just this basic sharp model. If you wanted to get TI-36X, that's nice. I think the 30s have some of the business functions built in, so those are pretty nice also. You don't really need like a real expensive calculator. You don't need a graphing calculator. Ideally, $20 or less would be kind of your price point, which is great, I think. 'Cause I know the graphing calculators can run up to $100 in those, which is kind of silly, but yeah. When you can get a laptop or Chromebook or whatever for less than $400, why is a graphing calculator that only has 2 colors, basically on and off, still costing us $100? And that's a very strange question. But yeah, just one of the basic TI models. If there's one that you think will work well with your business classes, beyond just this one, that might be a good one to have. Yeah. So we can go ahead and divide 96 by 12. I believe that's 8. Just making sure. Yeah. No, that's not true. The more money you spend on the calculator, the less money you have. That's the rule. So 8, we'll just split that again into 4 times 2. So this one we end up using both of the rules. Sorry. Square root of 4 times square root of 2. So it's 2 root 2. Okay. So in this case, the rule is that the square root of a divided by the square root of b is equal to the square root of a over b. So we're able to combine this into a single square root. We complete that operation. And then this 8, since it's not a perfect square, we go ahead and simplify it using the process that we already talked about over here. So I do have some homework for you today. This is on page 41, which is the homework for section 1.5. If you have the ebook instead of the physical copy, the sections should be the same. I'm not quite sure if the page numbers are identical, though, unfortunately. Let's see. There's a few things we didn't talk about, like with signed values, but I'm hoping you'll be okay. We'll go ahead and look at 1, 7. And 15. Hmm. 29 and 31. And 33. $37. What I'll do, Luke, is I'll go ahead and take a picture of this page out of my textbook and upload that image to Canvas, just in case someone doesn't have the book yet. Plus, I haven't connected the book to our course yet on Pearson, so you won't be able to connect through Pearson yet, unfortunately. You should be able to access it through your 1324 course, because this is the same textbook. But I'd prefer to give you the means to do that through our course, not through the other one. So. If you're having problems with this, it's all right, because it's a lot of stuff that we went over today, and I understand if you're not feeling terribly comfortable at the moment. I do want you to practice on these, and you can look back at this video to see if looking at the material again helps you. But also, feel free to contact me through Canvas. If you have a question, I can point you in the right direction as far as how to answer a problem. But yeah, let me know if you are having some difficulty, if there's any specific thing or if it's a more general thing we can talk about. I'll figure that out in a second. I'm sorry, guys. Let me get the problems written down first. Yeah, I think what I want to do is I'll go ahead and set this up in Canvas. So if you don't want to write these down right now, that's fine. But I'll make sure I get them set up in Canvas so you can complete the homework through the My Math Lab, and that way you won't have to worry about writing down the answers or submitting the answers. If you do it in the My Math Lab, it'll basically take care of that for both of us. So yes, in the textbook, but don't worry about it just yet. I'll make sure I get it set up in Canvas, and then I'll attach a due date to it, so y'all can go ahead and get working on that. Do you have other questions? All right. Well, I hope you all have a good rest of the week, and a good weekend. Take care, rest of the day, and all that. And I'll set the due date in Canvas, so don't worry about that just yet. So y'all take care, and I will talk to you again on Monday. So have a good day.